Hi everyone, it's Mr. Bowman, and in Chapter 12, the last chapter that we have to cover before we start reviewing for the AP exam, we're going to cover two topics. One is going to be inference about the least squares regression line, and then the other one is going to be finding lines of best fit when the data is not linear, what we have to do to linearize it. So we're going to start with the inference, because we've kind of been in that mode, and that's the way it's laid out in the chapter. And so the basic idea is this. If we have a set of sample data from a population, and that sample data showed a linear relationship between the explanatory and response variable, we would use a least squares regression line to model that data and then predict the y values, the response values, from the given x values or explanatory variables. Well, that's based on sample data. What we really want to know is there a true linear relationship between the explanatory and the response for the population that sample represents? Or is it possible that the linear pattern that we see in our sample data, our sample scatter plot, is just occurring by chance? So we're going to address how to weigh the evidence, so to speak, to see if that relationship is truly linear or not. To start with, in this example, we're going to look at the population data for the relationship between the duration of an eruption in minutes and how much time between sequential eruptions in minutes for Old Faithful from July of 2005. So this scatter plot represents the entire population in this case. There are 262 points on here, and we're going to start out by just doing a little review here, and it says describe the pattern in the scatter plot, and as you remember, strength, outliers, direction, shape, not necessarily in that order. And so if we were to take a look at this scatter plot, we would say that there's a strong positive linear association. You would also probably point out this unusual situation here is that there are two distinct groups in this association, but overall the data appears to be linear. Part B says, do you think a line is an appropriate model? Discuss the methods we have to assess linearity. So what we would do is we would start by making a scatter plot. We would then make a residual plot. Remember, in the residual plot, we don't want any patterns. We would look at the values of r, r squared, and s. And if you're thinking, boy, we haven't done that for a while, well, we'll go back and we will review that later on. So moving right along, in this case, the least squares regression for this data is that the interval is 13.3 times the duration plus 33. Explain the meaning of the slope and the y-intercept in the context of this problem. Okay, so remember what we're saying here is that this is the population line of best fit. As the duration increases by 1 minute, the interval will increase by 13.3 minutes. If it were the sample, then we'd have to say as the duration increases by 1 minute, the interval is predicted to increase by 13.3 minutes. The y-intercept in this case is when the duration is 0. That would tell us that the interval is 33. That probably does not make any sense in this context. Part D asks, the coefficient of determination for this least squares regression line is 0.85. Explain the meaning of this value. So 85% of the variation in the response variable, the intervals from the average interval, can be predicted by the least squares regression line. And that's how we interpret the coefficient of determination. So here's where we're going to talk a little bit more about this idea of a population line of best fit versus a sample line of best fit. This is the entire population's worth of data, and this is the population line of best fit. and we use some slightly different notation. And some of this we'll explain later, but what we say is that the mean for y is equal to alpha plus beta x, where the mean for y is the predicted or the response value, alpha is the y-intercept, and beta is the slope. This line of best fit for the population is often called the true or the population regression line. So what we're going to look at next is kind of a contrived situation, but it should do a good job of getting the point across. So let's assume that from this population of 262 eruptions, we took a random sample of 20 eruptions. We would then plot that association as a scatter plot, and in this particular case, we got this sample data and this sample line of best fit. So the slope in this case would be 14.6 and the y-intercept would be 30.5. In part B, it says, if we selected another simple random sample of 20 data values, would you expect the same values for the slope and y-intercept for the sample data's least squares regression line? Discuss your reasoning. Well, clearly, since we're random sampling, and if we were to take a sample of size 20, there are lots and lots of samples of size 20 from the 262 in the population. So we should say, no, we don't expect to get the same values for the data in our sample or in another sample, and therefore we don't expect to get the same slope and y-intercept. So this gets at the idea of sampling variability. We know that there would be variabilities in these sample values. The sample slope and sample y-intercept would change from sample to sample as long as the data was randomly selected. We can consider this an unbiased, we can consider the slope and the y-intercept from this sample as unbiased estimators of the population slope and y-intercept. And just like we have before, we could talk about the sampling distribution of sample slopes and the sampling distribution of sample y-intercepts, but we're going to focus strictly on the sampling distribution of sample slopes. And if the sample slope B is an unbiased estimator of the population slope beta, then the mean of the sampling distribution of sample slopes is equal to the population slope. So before we do inference for the population slope, we are going to talk a little bit more about the sampling distribution and some of the conditions necessary to do inference for the population slope. One of the conditions is that the data comes from a well-designed random sample or from a randomized experiment, just like it does for any of the other types of inference that we're doing. So to check this condition, make sure your data is a random sample from the population or that there was random assignment for an experiment. Another condition is that the data needs to be linear. And again, we will not be getting a look at the entire population, so we are going to have to check the linear condition based on our sample data or our sample scatter plot. But before we get into how to do that, I want to talk about the population scatter plot and what's actually going on if it's a linear relationship. So what we're going to do here is we're going to look again at the population scatter plot, and we're going to pick a duration value of 2, and you can see that at a duration value of 2, it appears that there are various y values or intervals, and that turns out to be true. And what you see here in this histogram is simply the intervals for all of the sets of data in the population or pieces of data in the population that have a duration of 2 minutes. If the data for the entire population does in fact follow a linear model, then the population line of best fit, mu y equals alpha plus beta x, will pass through the mean of this distribution. And that will be true for every single duration. Every single duration could have multiple interval values or response values, and the population line of best fit, if it's truly a linear association, will pass through the mean interval length for each of those various durations. I'm simply pointing out what it looks like for a duration of 2 minutes. And that's why we have this particular notation here, that mu of y is equal to alpha plus beta x. What we're saying is that for a given x value, 2 in this example, that the y value will be the mean of those y values. So mu of y, using mu for the population. In this particular situation, again, we know the population, and the mean of this distribution of interval times in minutes is 56.2. So when x is equal to 2, the mean y value is 56.22. In other words, the point 2 comma 56.22 is on the true or the population least squares regression line. This graphic here is to illustrate exactly that. So what you see is you see a whole bunch of x values, call them x1, x2, x3, x4, x5, and so on, which represent various durations. For each of those durations, we have a distribution of interval times, and if the population line of best fit, if it's truly a linear relationship, then the population line of best fit will go through the average value for the response variable, or the average y value for each of those. So how do you check the linear condition based simply on the data? We do it exactly the same way that we've done it all along when we are looking at least squares regression line. So what we do is, the first thing is to put the data in our calculator and make a scatter plot. If the scatter plot looks reasonably linear, then the next thing we're going to do is we're going to take a look at the residual plot. So I am going to skip ahead, because you all know how to do that. I'm going to skip ahead to where I've actually done that here, and I am going to show you what that actually looks like. So the data is put into list 1 and list 2 of my calculator. I find the least squares regression line. The relationship appears to be fairly linear. I look at the residual plot. The residual plot looks to be pretty random, except for maybe this one value right there. Other things that we could look at would include the value of r and r squared. Those alone are not adequate to look at, but in conjunction with the linear scatter plot, the random pattern on the residual, it looks like it's very reasonable that this sample data is linear, and since it was randomly selected, it should represent the entire population, and therefore the population data should be linear. One other thing that we could look at would be the value of S. S is the sample standard deviation for the response variable, or the deviations from the line of best fit. So what we're saying here is that the average error in our prediction for our sample is about 6.77. And you can go back to the previous page a little bit, and you can see that we are predicting intervals, so an error of 6 to 7 minutes doesn't seem terrible. It seems worst case it's about 10% of the overall predicted values. Not too bad. But that's how we check the linear condition for, or using our sample for the population. Independence condition. It seems like we have an independence condition no matter what kind of inference we are doing. So are the individual observations independent of each other? We can invoke the 10% condition if we're sampling without replacement, or if the context is such that we are randomly assigning treatments, then we can use that to determine independence. The next condition is the normality condition. This one's quite interesting, and it goes back to these distributions right here for the various x values. So what we want is we want each of these distributions for a given x value to be normally distributed. Now, you cannot tell that by looking at the sample least squares regression line, and you really can't tell it even if you're looking at the population least squares regression line. So what we do is we make a normal probability plot of the residuals. The idea being that each of these distributions have the same amount of variability, and if they are normally distributed, most of the values are going to be close to the mean. Some of them are going to be further away. And if we're randomly selecting data from the entire population, the residuals should be normally distributed. So after we find the least squares regression line and determine if it's a linear association based on the data, our calculator automatically calculates those residuals for us, which is shown down here in the lower left. The next thing we're going to do is we're going to make a normal probability plot of those. So we go over to our calculator and we change the data list to the list resid. And you can only do that after you found the least squares regression line, because the calculator will calculate the residuals for you. So you can see from this plot, this normal probability plot, that there appears to be some curvature in it, and that would indicate that we do not meet the normality condition. The last thing that we need to check is the equal variance condition. And again, that goes back to this plot right here. These distributions of y, or interval values in this case, should have equal amounts of variability. And the way we figure that out to see if we meet that condition, or see if it's reasonable that we can assume that we meet that condition, is by looking at the residual plot. So as part of the linearity condition, you're going to look at the residual plot, but you're also going to look at the residual plot for the equal variance condition. What should you be looking for? Well, if we have equal variance, then we want a random scattering of points like we see over in residual plot B. If we don't see that, maybe we see this fanning out pattern where as the explanatory values increase, the variance about the line of best fit increases, or if we see any pattern at all, really, then we don't meet the equal variance condition. So, in summary, the conditions that we have to check: linearity, independence, normality, equal variance, and randomness. Not necessarily in that order. For those of you who like things to help you remember, liner. If you want to write it as linear, you could do that, and the A could stand for and. Once all of the conditions for regression inference are met, we can proceed with inference. Again, if you don't meet all the conditions, point out that you don't meet all the conditions and do the inference anyway. And the way we do that inference is the sample slope plus or minus the critical value times the standard error of the sample slope. Usually, these values are going to be given to you, or you're going to be able to calculate them on the calculator. So you're going to see some formulas here in a minute that you don't need to get too worried about, but you will need to know how to read this off of computer output. So here's the computer output for inference for slope for our particular example. And if you recall, the way we read this is that we have these variables here, intercept. So the coefficient, or below the coefficient in the intercept row is the y-intercept. The duration is the explanatory variable, and its coefficient is the slope. So there's our slope, 14.19. The standard error, SE subscript B, the standard error of the slope, is given right here. And the other stuff we will talk about later, the t ratio and the p-value. The stuff in the intercept row you don't have to worry about because we are not responsible for knowing inference for the y-intercept. Even though you won't be responsible for it, I do want to show you how you can calculate SE of B, the standard error of the slope, the standard deviation of the sampling distribution of sample slopes, actually the estimated standard deviation. S is the average deviation about the line of best fit. That's our error in our predicted values. And that is calculated by taking each y value minus the predicted y value, squaring it, summing all those up, dividing by n minus 2, and then taking the square root of that. To calculate the standard error of the slope, we take S and then we divide it by this term right here, the summation of x minus x bar quantity squared. Again, you'll be given that value and you won't normally have to find that, but those are the formulas for that. So, how do we actually calculate the confidence interval? So the first thing we have to do is recognize that the sampling distribution of sample slopes is a t-distribution, and if we are going to construct a confidence interval, we need a sample slope. So we have that right here, 14.19, plus or minus a critical value, which is based on the degrees of freedom and the level of confidence. So in this particular situation, we want a 95% confidence level. We have a sample size of 20. So for inference for the slope, we use n minus 2 for the degrees of freedom. And as you recall, using inverse t of 0.975 will give us the correct value, the correct critical value. That turns out to be 2.10. You should verify that. And then we plug those values in, we show our work, we get our confidence interval, and then we interpret it in context. So it goes like this. We are 95% confident that the true slope beta of the population line of best fit relating duration to interval lies in the range from 11.34 to 17.04. The last thing I want to show you before I have you practice a problem on your own is how to do this on your calculators. So the first thing you have to do is enter the data into your calculators. I typically use list 1 for explanatory and list 2 for response. The next thing I want to do is hit stat, go over to tests, and find the linear regression t-int. We are going to talk about linear regression t-test eventually, but for today, linear regression t-int, select that, x-list, explanatory, y-list, response, count each one once, level of confidence. If you want, you can put the regression equation in y1, which will then quickly allow you to graph it along with the scatter plot. And we hit enter, calculate, and we get the confidence interval, the sample slope, the degrees of freedom, the sample standard deviation, i.e. the error in our predictions, the sample y-intercept, r squared for our sample, and r for our sample. And then you can also go back to the scatter plot and get a graph of that with the least squares regression line in there just to verify that you're working with the correct data set. What I'd like you to do now is I would like you to pause the video and do the check your understanding problem. When you're done, come back on and we will go over it. All right, we're not actually going to check the conditions for this problem. We're going to talk about what they are and how to check them. So you need to check it's a random sample or the subjects were randomly assigned. That would be stated. You need to check that the data is linear. You can do that by making a scatter plot. I recommend doing that with the line of best fit, a residual plot, the value of R, the value of R squared, the value of S. You could check independence by invoking the 10% rule if we're sampling without replacement, or if you are randomly assigning subjects to treatment. Normality of residuals. You have to find the line of best fit to get the calculator to find the residuals for you. Once that's done, you can make a normal probability plot of the residuals. If that is linear, then we can assume that we meet the normality condition. And then the last one, the constant or equal variance of the residuals. Take a look at the residual plot. There should be no pattern in it. When you get all done with this problem, there are 6 degrees of freedom. Here's the information that you need to show for your confidence interval. Notice when you use the t-int function on your calculator, it does not give you the critical value, so you are going to have to look that up so you can show that work. And then you have to interpret that interval. So we're 95% confident that the slope of the line, population line, for predicting pack weight from body weight of all high school students lies somewhere in the range from 0.0215 to 0.1601.